we're reaching the end of helicopter performance and helicopter aerodynamics in forward flight. So we are still in steady level flight at a given forward velocity, and we want to produce a certain amount of thrust, and we want to tilt the rotor disc so to produce a certain amount of propulsive force. Until now, we did everything just a rotor alone. But many times the fuselage produces a small amount of lift or perhaps a small amount of download, depending on the situation. So we need to take into consideration what happens to the helicopter when you include the fuselage aerodynamics into consideration. So we will show you a quick first order way of correcting for the presence of the fuselage while trimming the rotor in this set of slides. So by trim, we mean that we are going to look at the operating conditions of the entire vehicle now. So you're not only including the main rotor, but also we are looking at the tail rotor. And of course, we are including the fuselage. By fuselage, we mean the empennage, and also we mean the landing gear. And of course, the hub that connects the rotor to the fuselage. So all of these things are there. Unfortunately, the equations ended up are all nonlinear. Fortunately, they are algebraic. And they are all coupled. So when we know that when you have a coupled system of equations, if they are nonlinear, you iteratively solve for it. Assume a value, then change, see what happens, then change the value, keep iterating until you get to the final answer. So we're going to also outline the iterative procedure, how this is done in these slides. So let's take a helicopter in forward flight. It's flying at a V infinity. The tip path plane is the tip here to tip here, viewing the helicopter from the pilot's left. So this is the inclination of the tip path plane. So the angle between the red line and the tip path plane is called the alpha tip path plane. Okay. Now we know the rotor produces an H force in the X direction behind the pilot. We had an analytical expression for the H force derived earlier on. And tail likewise will have a tail H force. And of course the fuselage has got a huge amount of drag. So the fuselage here, the empennage, which is made of vertical tail, horizontal tail, the landing gear, and also the hub. This hub sometimes can produce as much drag as the rest of the vehicle. So the total drag is therefore the fuselage drag plus H force on the main rotor plus H force on the tail rotor. So the rotor has to produce the propulsive force forward to overcome all these effects. How about lift? This is the lift produced by the fuselage. We will assume it's at the centroid here, okay, center of gravity here. This is includes the fuselage lift and any empennage lift. Okay, if you have a small horizontal tail, and it's located in here, so it's producing an upward directed lift. Say, sometimes you have a small wing, sub-wing underneath the fuselage, which is used to carry extra fuel tanks, munitions, and so forth, radar, electronic equipment, and all those things will be producing also lift force. On the other hand, they may also produce a negative lift, downward directed lift. So whatever it is, this is the lift force, this is the gross weight. Therefore, the vertical force that the rotor has to generate is gross weight minus lift generated by the fuselage. So this is the vertical force. So the rotor has to produce an horizontal force to overcome the drag. It needs to produce a vertical force to generate the desired lift. So what it does is it tilts the disc forward so that the forward component of the thrust overcomes the drag of the fuselage, H force from the main rotor, H force from the tail rotor. The vertical component of T, remember this is alpha tip path plane, therefore this is 90 minus alpha tip path plane. Therefore, if you draw a vertical line here, this would be alpha tip path plane. So the vertical component is T times cosine alpha tip path plane is the vertical force up. So you can solve for tan alpha tip path plane is this number. So this is how much the pilot needs to tilt the tip path plane to balance the vehicle. Now, unfortunately, it contains lots of stuff in here, which depends on the vehicle orientation, fuselage angle of attack, for example. Just like an airfoil, if you pitch it up or down, the drag will change. If you rotate the fuselage up or down, it's going to produce drag force and also lift force, depending on its orientation relative to the oncoming free stream. So what is normally done is they will do the lift and drag characteristics of the fuselage offline. So they will take a fuselage, which means they take out the rotor, they have a hub still, they have the landing gear, they have the empennage, they probably remove the tail rotor, then they will compute the drag as a function of alpha. If the geometry is well defined, if the model is available, they may do it in the wind tunnel studies. If you don't know, if you're doing a conceptual design or early stages of preliminary design, you may go to CFD and say a big prayer that you're getting right numbers. Of course, once the prototypes are available, you can gather this data indirectly or extract it from the flight test data. Okay. So you have a number of ways of extracting the fuselage lift and drag as a function of its angle of attack relative to the oncoming free stream. Now, we look at what are the factors that control the fuselage angle of attack. First thing is the tip path plane, which we control by the pilot's action. Blade flapping dynamics. The pilot puts in theta naught, theta 1c, theta 1s. The blade response is beta naught, beta 1c, beta 1s. Now, the downwash, that means the main rotor pushes air down. So you have an oncoming forward velocity. So forward velocity plus this downwash produces a tilted flow as it approaches when it hits the airfoil rotor, when it hits the fuselage. Finally, the shaft mounted on top of the fuselage is inclined at an angle. So all of these things affect the fuselage angle of attack. We're going to show you quantitatively how this happens. So let's go step by step and see what happens. First thing is the shaft inclination angle is the inclination of this shaft with reference to this axis. This is your flight path axis, or the fuselage reference plane some x-axis. This is the y-axis. This is the angle that we have defined. Notice that many helicopters will already have it tilted forward so that the tip path plane is roughly perpendicular to the shaft. Okay. That means 1 per rev is cancelled. Beta 1c, beta 1s go to 0. So the tip path plane is the same as the shaft plane. Okay, that's the ideal situation. So they will have a built-in IS, or the incident angle, that is built in like this. Now, oncoming free stream is coming this way. This is the alpha tip path plane, is the angle between oncoming free stream and the tip path plane. This is the alpha shaft. Therefore, alpha tip path plane is alpha shaft plus beta 1c. Okay, so this is the alpha tip path plane. Okay. So the shaft angle, that means how is the shaft oriented relative to whatever, relative to V infinity, that's the alpha shaft. Okay. So this is the shaft plane, the free stream, so this is the alpha shaft. This is the blade flapping response, beta 1c, that defines the alpha tip path plane. Now, angle of attack of the fuselage, therefore, is alpha tip path plane. We want to tilt the fuselage forward. Effectively, we are tilting the this particular shaft forward. So when you change the alpha tip path plane, alpha shaft is changing. So alpha shaft is alpha tip path plane minus beta 1c. Okay. But remember, you have this IS, so we don't need to tilt the shaft forward so much because it's already tilted forward by the amount IS. So we subtract off that IS. And then this is the correction into the alpha tip path plane because of the downwash. Remember, the downwash is coming down this way, normal to the rotor disc. Therefore, it changes the alpha tip path plane by an extra amount, okay? Because the velocity vector changes slightly more inclined because of the downwash extra velocity that the rotor is generating, pushing the air down this way. So that extra velocity, extra angle is V over V infinity. So this is the alpha fuselage. Now, we were talking about the trim or iterative process, so this is how it'll work. Okay. You'll first assume an alpha fuselage, which is 0, is an initial guess. Okay. You start with an alpha fuselage 0. Okay. That's just a starting guess. Okay. Now, you go to the internal data and find what is the lift I'm producing, what is the drag I'm producing at that alpha, at that forward velocity. Okay. So you get that expression from a internal data table lookup. So once you have it, now you go up here and you say, okay, I know my fuselage drag from my table lookup I just got. I have the rotor has to produce at least to overcome that fuselage drag. We don't know this expression yet because we don't know the rotor dynamics yet. So we can set this to 0. We will have to compute the H of the tail rotor based on the thrust generated by the tail rotor, which requires the torque. We are overcoming the torque exerted by the rotor on the fuselage by producing a moment. So we don't know this either, so we have thrown all of this away. So we get a first guess of the total drag. And since we have the lift generated by the fuselage from a table lookup, we get a first guess of the vertical force. Therefore, we get a first guess of the thrust. So we know the vertical force we need to generate. Propulsive force we need to generate. We generate the thrust. Okay. So that's the first thing you do. So compute the needed thrust. So thrust is approximately GW minus LF even, crudely, because you have looked at the LF here. Once you find the thrust, you know the CT, and you also have an estimate of the alpha tip path plane. Remember, you have a first order estimate of the drag, which is just the fuselage drag. You have the estimate of the lift. So you know the alpha tip path plane. Fuselage drag, you have this expression here. This is not known. So you have a first order estimate of alpha tip path plane. Then use our previous set of slides, knowing the CT alpha tip path plane, you see trim the rotor like we did before. When you trim the rotor, you'll get the CQ, which is the main rotor torque. You'll get this H force from the main rotor. Once you have the main rotor torque, we know the tail rotor thrust you need to overcome the torque. So if you know the distance between the main rotor shaft, the tail rotor shaft, tail rotor thrust times this distance is what is needed to overcome the main rotor torque. This is the anti-torque that we are generating. So once you know the tail rotor thrust, you trim it as though it's a standalone rotor, and you find a tail rotor H force. And by the way, when you're trimming here, you get also a beta 1c. Once you have the beta 1c, of course you also have the tip path plane angle. Now recompute it, alpha f, based on the beta 1c, alpha tip path plane angle. For that particular thrust, what was the induced velocity, Glover's induced velocity? You recompute the alpha f. So you started with alpha f equal to 0, you've gotten a new alpha f. Blow this back in here, keep rotating until everything has converged. Once this is converged, you not only have the vehicle balance, but you also have the main rotor power, you have the tail rotor power, you have the parasite power because you have the vehicle drag times V infinity, you have the transmission losses, then you get the total power. So you also get the power as a byproduct of this iterative process. Now we are going to slightly change the story and say what happens, you lose the power. The engine is lost the power, so now you are trying to auto-rotate. So what the pilot will do is, later on we will see, the pilot will tilt the rotor disc backwards so that when the wind hits the disc, it produces like a wind turbine-like rotation, which we call an auto-rotation. We will visit it when we talk about vehicle performance. So what happens is you are producing the blade rotation to maintain its RPM. But the actual power that you need is coming from your potential energy. We don't want to lose the kinetic energy in the rotor, so when the rotor is spinning, you're losing altitude. So the rate of descent is important. How rapidly I'm descending at a given forward speed. So you want to know when you're going to hit the terra firma, when am I going to hit the ground. So we want to know what's going on. So we're going to look at the situation when you have the auto rotation. So the power is supplied by the rate of change of the potential energy. That means the weight of the vehicle times the vertical descent velocity. So taking a look at it, so the vehicle is vertically descending down. It is oriented this way. The disc is tilted slightly back. When the wind hits it, which is the V infinity plus this rate of descent, this total wind hits the rotor disc, it keeps it to auto-rotate like a windmill, keeps it spinning. So it's producing thrust, but now it is producing a rearward directed force. You still need a lift. You need from the rotor. Fuselage is producing a small amount of lift. So these terms, we have seen all of these things before. Fuselage is producing drag. This drag is along now the total velocity direction here. Tail rotor is in this direction. Lift of the fuselage is perpendicular to this total velocity vector. This is the H main rotor. Now the rotor is producing some thrust. Okay. So first of all, the descent angle chi is the vertical velocity, which is the rate of descent, the vertical direction, divided by the horizontal velocity parallel to the ground. So this is chi. So how do we model this? How do we trim the rotor? What does the pilot do under these situations? So we go here. First thing you notice is now your weight is providing a small amount of propulsive force forward. So you have a W sine chi forward. Therefore, your rotor thrust plus this gross weight times sine chi is balancing the drag. Okay? So gross weight is helping you. It's producing a propulsive force forward in addition to the rotor itself, helicopter rotor itself. So helicopter rotor propulsive force plus weight pointing forward component in the direction of the descending velocity direction, total direct velocity direction. So this is the main rotor fuselage drag, main rotor H force, tail rotor H force, and force from this particular picture in here. In the vertical direction, you have not a full gross weight, but you have a gross weight cosine of chi. Okay, that's balanced by the thrust in this direction times lift force. So the thrust in that direction is T cosine of alpha tip path plane equal to this quantity. So when we do this, you get this value. This is similar to what we saw before, except now you have this rate of descent showing up in here. So if chi was 0, we'll go back to trimming when under power. So when you lost the power or when you're under partial power, chi becomes another variable. So now we want to descend as slowly as possible, okay? Because so we don't damage the vehicle. We want to descend gradually, so we want to make this chi as small as possible. So what do? So you assume a rate of descent. Okay? That means you assume a vertical velocity. You're still traveling in the forward velocity. You don't want to lose too much forward speed. So this is fixed. You assume a rate of descent, so that gives you the chi value. So chi value is known here. So put that expression here, then trim the whole thing like you did the fuselage before, with the fuselage effect before, which we saw a few slides earlier here. Okay. So this is what we had done before, but now you have a gross weight sine chi term, gross weight cosine chi term in here. Other than that, the process is very similar. So this iterative process is done. So assume a descent rate, then iterate on the fuselage angle of attack like we saw earlier. Now once you have the power needed from the main rotor plus tail rotor plus transmission losses, this power needed is supplied by loss of the potential energy. So if you divide this total power by gross weight, you'll get the rate of descent. So you assume the rate of descent, you got a new rate of descent. So repeat this process until power required equal to power available, your rate of descent equal to converges. Not only rate of descent converges, fuselage angle of attack converges, main rotor thrust, alpha tip pad plane, tail rotor, everything is converged. So this is the process that is used when we are descending under either partial power or under no power from the engine. If it's partial power, this loss of potential energy is only to partially overcome the power. Let's say one engine out, the other engine is still producing power. Then you use the rate of descent to compensate for the loss of power. If both the engines are out, you're getting zero power from the engine, so everything is coming from the loss of potential energy. So you could do this analysis with minor variation to look at descent condition. So now we have concluded the vehicle in steady level flight, forward flight. We have also looked at how to crudely account for the effects of fuselage in steady level flight. We have also looked at how to model when the vehicle is descending at a vertical descent velocity, or a velocity where it balances the power need considerations. So we have pretty much completed the rotor in a forward flight from an aerodynamic perspective. Now we are ready to tackle the vehicle performance. So we will stop at this point and take a break.